Okay, everyone but Angelina went through first semester. Things are almost exactly the same. This semester is first semester. So I will actually spend time privately with Angelina to explain to her what's different.
Okay.
Here's the syllabus, so you have everything. Unless you're in Physics 250 to take one of those. Here's Corso.
I'm here on top. I won.
All right, I'll get you. Here, check it out. According to that clock, he's still 15 seconds on. Okay, so that's the syllabus. There are some differences I do want to point out. So what's different? There is a group project. That should have been 3 and 2 there. Got the numbers wrong. Sorry about that. Group project. We have lab tomorrow. Okay. We have lab tomorrow. And tomorrow's lab will actually be an oddity that you'll be working in groups. And I think it's a lot more. There'll be one group report for each group rather than individual reports. But then the week after for lab, it will be the first of our group project days. And that day, what you have to do is you have to determine who's in your group and what your project is going to be. Otherwise, the time is yours. I'm giving you the day off, not specifically so you have to work on the group project that day, because you probably won't have the information you need for it yet, but so you have free time that you can reallocate so that the time you would have spent in lab can be spent at some point on the lab project. And then that will occur again later on. This one here is, I'm going to say tentative. We have some budget constraints here at Union College. And last year, the division decided we weren't going to do that. And I begged and pleaded and got permission. And so I was still able to go to the field trip, but I was the only class that went to the field trip. I have been afraid to talk to Dr. Wolf about it again because the budget is not any better this year. So we may or may not be able to go on that field trip, but I want to let you know now so that assuming we can go, you know that we're going to be missing school for roughly half of that day. I am at least trying to figure out how to add this website here, Perusal. Peruse all. It would never count toward your grade. It's not going to be extra credit if you do it. And so it's only going to be for people who are interested in seeing if that helps them learn. The idea is this could take the place of the reading quizzes. What Perusal is a place where, since our textbook is free, you'd have free access to it, you would have to pay anything. You can read and highlight the textbook and make comments and questions to your classmates and me, and then other classmates respond to those so that you can have a collaborative online study of the textbook. And I'm not sure if students would like or dislike it. And so the idea is to put it there as an option. And if students like it, then, if they feel like they're learning and then they use it, then that would be a good sign. If students are like, it's not worth the time, I would only do it if it was for points, then I just stick with what we have. It's not running right now. That is, I tried to set it up on Friday and didn't get it working properly. So it'll be a project throughout the week probably to see if we can get that up and running. Otherwise, things are pretty much exactly the same. So when is homework due? 11:59 p.m. Monday, Wednesday, Friday. Well, not Friday, because Friday it's going to be an hour before sundown. And I go, Angelina's like, really? And where do you turn it in? Expert TA. So that's money you have to spend, and I'm sorry. Hopefully the $10 option becomes something that we can use in the future instead of that. I was looking for another class using a different homework site. It was $70 a semester. So I guess I should be happy with the $10 a semester we're paying now, right? All right, plus 29. Yeah, it all adds up. Any questions before I actually start getting into physics? Go ahead. The cutthroats are holding on to them. Oh yeah, Alex, I got one up here for you. You just, yeah. For the people in Physics 252, you have two schedules, one that's specific to 252 and one that the people in 152 have, just so you can read and compare. Because the lectures are truly based on the textbook that the students in 152 have, except for Tuesday. But I tried to put the 252 chapters in the 252 schedule. Okay, electricity. Electricity was discovered a long time ago. This here says as early as 600 BC, before Christ, it was known that charge could be accumulated by rubbing fur on amber, and this charge could attract things. So here's the basic experiment. Fur. This used to be one fur, but it's degraded. This is a rubber rod instead of amber, but it's the same idea. So you rub these things, and then you can do cool things. Like, I don't know if it's going to work for my... Wait, I don't have any here. Forget it. These here are pith balls. Should do something to the pith ball. Yeah, not much. Maybe I didn't rub very well. Those of you up front can probably see that it causes a little bit there. Pulled it out without me touching it. But it's not as impressive as I'd like it to be. Let's try this thing in back. This thing back here is called an electroscope. What it has is a bunch of metal, a pin holding a metal vein. And so I'm going to touch the rod to the metal. And you see, yeah, it definitely did something, right? If it made it move, what does that tell you using your first semester knowledge? There was a force. There was a force. The force caused the motion. So there was something going on here. Now I touched it. I'm going to actually touch it with my finger. Oh, look. My finger made it come back. I'm going to bring this up here. Bring it close. Touch it. Something major happened when I touched it. So as early as 600 BC, this had been observed. Fast forward a whole lot of years. In 1600, this was known as the phenomenon was named after amber, which is electron in Greek. So you guys, you've taken chemistry probably for sure. So you've heard the word electron. It's a Greek word for amber because they observed it with the amber rods. I know I'm using rubber, but same effect. And so then in 1729, missed a digit, couple, they identified some things conduct electric, whatever it is, and some don't. So they call the thing that is involved a charge. We've already talked about the magnetic force. And what's the thing that is affected by magnetic force? What is it? Did I say, I meant gravitational force. Is that what I said, or did I say something different? I figured everybody should know the answer. What is affected by gravitational force? Well, gravity is the name of the force, but what type of stuff does it affect? Stuff with mass. And so mass is the gravitational charge. It's the charge is the stuff that the force affects. So here we have an electric force, and since it's electric force, we can talk about electric charge. And so some materials were conductors that allowed electric charge to go through them. This metal is a conductor that allows electric charge to go through. Some things are insulators. They don't allow electric charge to move on them. Now, this rod is an insulator. It doesn't allow electric charge to move. But when I rubbed it, it clearly had electric charge. So the charge was there, it just couldn't move. That's the difference between an insulator and a conductor. It's not the presence or absence of charge. It's the mobility of the charge. So this here is an insulator. Metal is a conductor. If I touch the metal, electric charge will spread. And so now I took some of the charge off that. You can see the separation got smaller. The force pushing them apart got smaller. Why? Because some of the charge is now on this. So now I can put my finger on this, make it so there's all the charge goes onto my body. Then I bring this over, and I can get a little bit of the charge back on there. Not very much, it appears. Yeah, hard to see that worked. I am notoriously bad at doing these demonstrations. I don't know why. Well, it was later determined that you could take a glass rod and rub it on silk. Now, my shirts aren't silk because I'm not that kind of guy. I'm not the kind of person who spends money on clothes. My wife does, sadly. And so I can do this and bring it up here, and I touch it. And okay, that did something right. So I definitely transfer some charge there. If I bring this up here, bring it up close, and don't see too much of an action when I bring it up close. Now let's go back to this. Making a mess. Bring this up, and when I bring this up, it gets smaller. So there's two different kinds of charge because it had two different effects. So we had two kinds of electric charge. And Benjamin Franklin, great American physicist, randomly decided to say that what was on the amber, i.e. the electrons, had a negative charge. So he just randomly made the decision that electrons have a negative charge. And so now we understand charge a lot better, and a lot of people say Ben made the wrong random decision. If he would have chosen the other way and said electrons were positive, we would avoid a big argument about current, which is the motion of charge. So that's a background on the discovery. And I've talked about this in its entirety. And one of the basic rules that have been determined about charge is that charge can be neither created nor destroyed. In physics terminology, that means charge is conserved. Now, up to now, you guys would have assumed, except for I told you otherwise, that mass is likewise conserved. You can't create or destroy mass. But the truth is, you can create or destroy mass. Mass is simply a form of energy. But charge cannot be created or destroyed. As far as we know, it's always conserved. So if charge is always conserved, if I started with this rubber rod and it was neutral, what does neutral mean?
It is the same amount of positive charge as same amount of negative charge, so electrons and protons.
Electrons and protons, but she's perfectly correct. Neutral means you have equal amounts of positive charge and negative charge, so the net charge, the total charge, is zero. So this started neutral. And then I rubbed it with some of this fur, and this became negative. If this became negative, what had to happen? Okay, one answer is protons move. Now, with further research and study, scientists have determined that's not it. It would have been a perfectly good option, except for it's not what happens. The protons are fixed in place, for the most part. But electrons are whirring around in some crazy cloud, and the electrons can be added or removed. So if I took this rod and it started neutral and then ends up negative, and electrons have a negative charge, what happened to the electrons with regard to this rod? They got added to it to make it negative. So I must have had electrons that were originally on the fur were rubbed off of the fur onto the rod. And so how does that work? Basically, and this is what one group did for their project a few years back. In the lab guide, you'll see a list of the recent projects. It's there, I think. Basically, the rubber has a certain amount that it's holding on to electrons, right? You talk about electron affinity or something like that. And the fur has a different amount that's holding on to electrons. And when I rub them, the one that's holding on to electrons more weakly will have a net loss of electrons to the other one. And so when I rub the fur and the rubber together, electrons were lost by the fur and added to the rubber. When I used my shirt and the glass rod and went the other way, the glass rod was giving up electrons that went into my shirt. So that's how we charge things. We can't create or destroy charge. We simply move it from one object to another. So once again, I can go right past that. Through careful research done by, Charles d'Augustin Coulomb, I believe, is the one who did the most research on this, and hence his name is used for the unit of charge. The unit of charge is the Coulomb. And the law for the force due to electric charge is called Coulomb's law, because he's the one that derived it. Through careful study, you have to go to, like the Millikan oil drop experiment establishes what the basic amount of charge is. And we find the basic amount of charge is 1.602176565 times 10 to the minus 19 coulombs, good to that many decimal places. It's not an exact number. There's some uncertainties, but that's the number of decimal places we have for, oh, come on, for the charge of an electron. There is a way. There we go. An electron has a negative charge, though. E is the symbol we use for the magnitude of charge of an electron. So the actual charge of an electron is minus E because it has a negative charge. So anytime you see a charge of E, that E is a positive number. Now notice the electron charge 1.602 times 10 to the minus 19 coulombs. An electron carries an extremely small amount of charge. Or conversely, the Coulomb is an enormous unit. So when we do problems, we'll often talk about picocoulombs or nanocoulombs or microcoulombs. Maybe millicoulombs, but that's a pretty big charge in and of itself. So there's a whole lot of electrons involved with a Coulomb. How many electrons make up one Coulomb? Very simple question. Q is the symbol for charge. C is the unit, Coulomb. Better put a minus. How many electrons, electrons, is that? Anyone? Bueller? Bueller?